The Eastern Avenue Adaptive Signal Control Technology Pilot Study. The Regional Transportation Commission of Southern Nevada is the MPO, the Metropolitan Planning Organization for the Las Vegas Valley. But unlike most MPOs, maybe even all MPOs, we have some additional duties. We also operate the transit system, the fixed route and the paratransit system. And we are also the regional traffic managers. We operate the traffic signals on behalf of our member agencies and the ITS devices on the freeways for the Nevada Department of Transportation. So we have fingers in a lot of pies. So we were really interested in trying to, demo, come to understand adaptive signal technology. And we chose Eastern Avenue because it has kind of the reputation as one of those untamable beasts. The corridor study was done about a year ago, maybe a little longer than that. And they basically said that an adaptive signal system would not be that effective on Eastern Avenue. So, of course, we felt that was a challenge. The other nice thing about Eastern Avenue is that former to my duties at the RTC, I was the traffic engineer for the city of Henderson, who was one of our partners on this project. So I was really familiar with this piece of Eastern, and I felt, and once we got Ian on board as our consultant on board, we really felt that Eastern Avenue could benefit from adaptive, but it was a tough cookie to crack. A heavy commuter corridor, a lot of different land uses, schools, big box. It's a transit route, the tail end of a pretty significant transit route in the valley. Two major regional facilities run right through the middle of it. Hospitals, a lot of customer complaints. It's about evenly split between Clark County, unincorporated Clark County, and the city of Henderson. So they got a lot of complaints and a lot of pedestrian use driven by the land uses. This is just it's in the southern part of the valley, if you're familiar with the Las Vegas Valley. At the very end off the screens, about 15,000 rooftops, not entirely, but primarily a senior age-restricted area, but there are some areas that are not. So a large commuter population at one end, and then regional transportation facilities on the other. So the movement north and south along that corridor is really important, but there are an awful lot of competing interests as far as cross traffic and access to high demand land uses. The deployment. You want to take it from here, Ian?
Yeah, sure. Thanks, JP. Thanks for that run into the project. So the deployment of the project utilized Rhythm Engineering's InSync solution. So here's a few snapshots of the new detection cameras being installed, part of the commissioning works, and then on the far right, actually switch on day. So on October the 19th, the system was switched on. So again, new detection systems in there, the InSync adaptive traffic signaling solution in there, and again, part of my role there was to study the before and after data to understand really what changed when the adaptive system was actually commissioned. The study itself utilized a number of different data sources, including again StreetLight Data for intersection delay analysis. We also had a number of Bluetooth detectors on the corridor, up and down, fully down east, north, south, and also on the major cross section with St. Rose Parkway on east, west. And also RTC Fast have their own automatic vehicle location probe data, which again was utilized for a lot of the north southbound movements to understand these changes. So not just a single data source, multiple data sources to corroborate the information to ensure the results are rechecked to ensure validity of that data. And if we look at some of the results of this data,
it was really important that the RTC took on an adaptive signal project, I don't know, 15 years ago, something like that. And it was frankly, it was not successful. And we did not want to have that experience again. Obviously, the technology has come miles since then. We're in generation, 6 or 7 now, and that was generation 1 or 2 then. But it was really important. We wanted to look more, not just travel times on the routes, and not just looking at the corridor. We really needed to understand what the effects were at the intersections, really look at the delay at the intersections and figuring out a way to measure that was really challenging. And that was the niche that StreetLight Data was able to fill for us. We really needed to prove that we were not only improving operations on Eastern, but we were not adversely, and in fact, maybe we were actually helping the intersections and the cross traffic. So that was really why we kind of reached out, and we're going above and beyond what you would see in a normal before and after study on an adaptive system.
No, thanks, JP. No, it's a good point to make, because I mean, you know, as a consultant, I've been involved in lots of these studies previously, and again, done lots of research in this study environment around, you know, before and after. And for the remit that that JP went for at the RTC was a really in-depth, detailed study using these multiple data sources to really understand, like you mentioned there, JP, that the you know, not only the corridor movement but also the effect on all movements, including the side streets. So it was a very in-depth study of that data use, which again, StreetLight Data helped in that environment vastly. Picking up some of the measurements that were captured really to show improvement. And previously the corridor run on a time of day on plan, using a fixed time with some detection on that as well, to look at some of the timing changes. But again, putting the adaptive on really spun this corridor on its head. And again, looking at these changes, so all these figures here with minus means improvement. And again, looking at, you know, northbound was a bigger improvement than southbound. But again, looking at the travel time on here, is again as a yearly change in travel time, there was an improvement of 483,718 hours, and an improved stop duration of 294,000 hours. So the measure here showed us that the travel time from end to end points, and this is looking from the full run of the corridor, and it was 14 intersections and about 3.1 miles. So this is the full corridor movement. So this is vehicles that did the full commute run, which was a high percentage of the vehicles on here. So again, looking at the changes on the corridor, we see a vast improvement in these journey times, in, you know, stop duration and travel time. And to look at this as a percentage change, and then we looked at the figures there in hours, but to look at this as a percentage change, and again, you see all these numbers in green here. So, you know, speed increases between 8 and 31%, travel time reduction between 8.6 and 24%, and the one big thing here is the number of stops. Again, putting adaptive in, and the way we measured this has really shown how much of a difference it made on the number of times a vehicle stopped. So stop delay, that's the actual number of times stopped in seconds, increased between 10% on southbound, 57 on northbound, and again between 37 and 69 number of times vehicles stopped. So again, a big improvement in the corridor itself. Specifically for the StreetLight data, again, as JP mentioned, we were really interested in the whole intersection and how the intersection has changed from all directions, all movement counts. Again, so previous studies looking at corridor improvements just looks at the corridor. So we look at that, you know, that end-to-end point, where for this study it wasn't. It was looking at all movements on intersection. How much is the effect of implementing a different traffic management system affected the actual corridor here? So utilizing StreetLight data at the far south end, and they are really close to each other, so we count them as one intersection. So we can see on here that the changes, some of the intersections improved the delay, and some was impacted by the delay, but an overall delay change per day gave us 53 hours of improvement in delay at that individual intersection, which gives us so just over 19,000 for the year. And again, utilizing the data, we can see how, you know, there's percentage split between the main north-south corridor and the side street data. So again, this gives a real understanding of the performance of that intersection and how the split in traffic is between the different movement counts. Because again, you know, we may improve the majority, but then some of the side streets, again, as you can see on the numbers in black, you know, we increased some of the delays, but the overall majority of the traffic was improved. And again, this utilizing this StreetLight data gave us those results to be able to sort this out and to really understand where we physically are in the data. my slightly out of focus pictures here, but this is a grab from the StreetLight Data platform, because I wanted to help people understand into how we actually utilize the data. So this is showing an intersection of Eastern Avenue and St. Rose Parkway, so one of the major crossroads in the project. So we were interested in, again, all 8 movements, all 8 signalized movements of an intersection here. So on the right hand side, you can see where we drew the physical detection zones. Again, looking at each, all the way across the corridor here, capturing movements in and out. And then on the left hand side, we can see the overlay. So each one of these zones we created as an in and an out zone, and then looked at the time taken to travel from point A to point B. Again, at all the movements required, so straight aheads and the signalized lefts, which gave us the results you see in this table here. The analysis we undertook gave us these results here. Again, timesing them out by the number of vehicles over the stop line to give us a real understanding of the corridor and how the corridor changed during that implementation. For the carbon emissions, again, this was a calculation done on based on the speed changes on the corridor. So the average speed on that corridor changed, and changed, quite a high percentage, which had a real impact on the CO2 emissions. And again, using the University of California graph on per vehicle emissions based on speed on the average American car, it gave us a significant 3.2 tons of yearly savings on northbound traffic based on the per vehicle trip changes. And for southbound, almost a ton of CO2 emissions, again, based on the University of California curve and based on the information we have from the system. Rounding up the results, really, again, we've got the split here between northbound and southbound movements. Again, some very significant figures here. And when we calculated these figures, again, typically we see a big improvement in travel time and in number of stops. But again, when you actually calculate them yearly, the figures look staggering. They also look unbelievable. When you say that on northbound traffic, so over 3 miles over the year, we've reduced the number of stops by 32.7 million, which again just seems too big, but it's actually, these are, again, the data used is not from a single source. We use multiple data sources to verify all this information here. So again, the figures seem staggering, but these are realistic figures that have been all calculated up.
Yeah, that the top one there, the improvement in on-time performance for our transit services. This was not one of the measures of effectiveness that were looked at the beginning of the project. This was kind of an unexpected benefit. This is the tail end, the southern end of a major route, and there are 2 time points. One going southbound, right at Pebble, which is in the north end. They come about in the middle into the corridor and then turn around. And just the improvement in traffic flow increased on-time performance by 4.6%. And this was using no transit signal priority, just the reductions in stops, the improvement in travel time reliability. There was so this was yet a third, actually probably a 5th data source that confirmed the results. So this was a really pleasant, unexpected surprise. The CO2 reductions, obviously, that's something that is hugely important. 3 million pounds per year, 330 cars off the roads. That doesn't sound like a lot, but this is only a 3-mile section, and there's about 10,000 centerline miles in southern Nevada, the Las Vegas Valley. So if you do the math, what did we come up with? It's like over 1 million cars, right? 1.1 million cars a year off the network. If you look at it, just doing some simple math. Obviously, the intersection delay result speaks for itself, and this is the real, Ian mentioned statistics that are too good to be true. This was one that we checked and double checked and quadruple checked.
Yeah.
But it's true that the $900,000 that we spent on this project in round numbers was essentially paid back in reductions in fuel costs and time costs of the commuters The payback period is 32 days. That's not a misprint. So, we're obviously very bullish on this technology, and we're very thankful to StreetLight for helping us prove this out in a way that I don't really think has been done before, at least to this level of detail. So, thank you for the opportunity.